All right, let's get into it. Today, we're taking a deep dive into coordinate geometry.
Yeah, it's a great topic.
We've got some source material here, and our mission, really, is to pull out the key ideas, give you a shortcut to understanding how we map space using numbers.
It's pretty amazing how such a simple concept at its core becomes so powerful. The source material really highlights this. It's basically using a pair of numbers.
Coordinate.
Exactly, coordinates, to pin down the location of a point, like giving everything an address.
An address tied to a grid, right?
Yeah.
Formed by those two perpendicular number lines.
That's it, the coordinate axis. It's the whole system that lets us, translate where something is into math, connects location with relationships.
So it's the bridge, connecting the physical spot to the numbers and how points relate in shapes and figures. The source also talks about variables, like in equations. Y equals mx plus c.
Right. Dependent and independent variables. It's pretty straightforward. If you set up the equation with y on its own, like y all a mx plus c, then y depends on whatever x is. So y is dependent.
And x is independent.
Yeah. But what's neat is how the source uses that other example, 4 by 5y plus 20 equals 0. You can rearrange that equation to solve for y, making it dependent on x, or you could rearrange it to solve for x, making it dependent on y.
So the dependency isn't fixed to the letter x or y. It's about how the equation is structured.
Precisely. It depends on what you're trying to express or solve for.
And the specific way we capture a point's location, that address, is using an ordered pair.
Exactly right. An ordered pair, written like AB. And the key word is ordered.
The sequence matters.
Hugely. The source nails it with 5, 7 is not the same as 7, 5. Different locations entirely. A is the first component, B is the second.
Makes sense.
And this order lets us set up equalities. If you have A, B, A, C, D, it absolutely requires that A equals C and B equals D.
Like the example they gave, x des 3, 6 equals 4, x plus y.
Yeah, that forces x des 3 to be 4. So x must be 7.
Yep.
And then 6 must equal x plus y. Since we know x is 7, it's 6 plus y, it's 5.
Which means I has to be -1. It's like a little logic puzzle built in.
It is. It neatly packages two pieces of related information.
Okay, so we've got variables ordered pairs as the addresses. Where do these points, these addresses, actually live?
They live on the Cartesian plane, named after Descartes, of course.
Right.
It's that flat, two-dimensional surface you get when you draw two number lines crossing each other at right angles at their 0 points.
The horizontal one we call the x-axis.
Yep. And the vertical one is the y-axis.
And the spot where they cross.
That's the origin, point 0 for both lines. The whole setup axis, plane, that's your Cartesian coordinate system, your map grid.
And every single point on this grid gets its own unique ordered pair, its coordinates.
That's the idea. The first number, the x-coordinate, sometimes called the abscissa, tells you the horizontal position relative to the origin, left or right.
And the second number, the coordinate or ordinate.
That tells you the vertical position, up or down from the origin, and it's always written in that order, x, y, abscissa, then ordinate.
So the origin itself, being at 0 on both axes, is just 0, 0.
All right.
And if a point is on the x-axis, say 7 units to the right, its x-coordinate is 7, but it hasn't moved up or down, so its y-coordinate is 0, making it...
Exactly. Or maybe 4 units to the left would be 0, 4, 0. The 0 in the y spot tells you it's on the x-axis.
And similarly, for the y-axis, a point 8 units straight up is 0, 8, 0 horizontal move, 8 vertical.
Perfect. Or maybe 2 units down would be 0, 2. The 0 in the x spot locks it onto the y-axis.
Now, these axes, they don't just cross. They divide the whole plane up, don't they?
They do, into 4 distinct sections called quadrants.
Quadrants.
Numbered 1, 2, 3, 4, usually counterclockwise, starting from the top right. And the source points out a really handy thing, the sign convention. Just by looking at whether the x and y coordinates are positive or negative, you instantly know which quadrant you're in.
Ah, right. So top right, everything's positive.
That's quadrant 1 plus stato plus.
Top left, x is negative, y is positive.
Quadrant 2 plus
bottom left, both negative.
Quadrant 3.
And bottom right, x is positive again, but y is negative.
Quadrant 4 plus swar. It's a quick visual check. Very useful.
So let's recap. We've laid down the basics, describing points with ordered pairs, plotting them on this structured grid, the Cartesian plane, with axes and these distinct quadrant regions.
Yeah, we've got the fundamental building blocks in place.
And this system, as the source hints, is what lets us start visualizing things like those equations we mentioned, turning abstract algebra into actual lines and shapes you can see.
It bridges that gap between numbers and geometry.
So, wrapping up, think about this simple idea, mapping points to number pairs. It seems basic, maybe, but this coordinate system, it's not just for school grass. It's the engine behind, well, so much.
Uh-huh. Everything from GPS telling you where to turn,
to how your computer screen draws images, how engineers blueprint designs, how scientists chart data.
It all comes back to this fundamental concept of giving location a numerical address, turning space into calculation, and calculation back into space. It's quite profound, really.